Hello, my name is Anmol Birring, and this video pertains to magnetic particle testing, but specifically I will be discussing these variables called B, H, and mu, which are referred in magnetic particle testing. So we'll have a quick discussion and then a demonstration, so you really get to get an idea what these are. So as you know, I is the current, B is the magnetic field in Gauss, H is the driving force, magnetizing force, which is number of turns times I, and mu is the permeability. So first thing is Ampere's law. Ampere law says that when current passes through a conductor, this one, then a magnetic field is produced, which is B. That's B. So we will transmit current and then we will check the magnetic field with a Gauss meter. So here it is a quick demonstration. So here is a quick demonstration, and I will pass the current in the wire and you will see the needle on the Gauss meter move. So here it is. This is the wire, and it's connected to a battery. And you can see the dial is here on the Gauss meter. And when I connect the battery, the current will flow in the wire and it's going to move. So here we go. See that? The needle move and I'm back to zero. Then again, I'll pass the current and the needle move and it shows on the Gauss meter back and forth. So this is simple Ampere's law, which means the current goes through this wire and then the magnetic field is produced. So the next demonstration will be on the coil and the solenoid, which is used for longitudinal magnetism. And here I will do a demonstration again, connect the wire to the battery and run the current through the wire. And we will check the magnetic field in air, where the permeability, relative permeability is 1. And then I will put a non-magnetic material, and then I will put a magnetic material, and you will see the response to the Gauss meter. And the magnetic field will be higher when I put a magnetic material inside the coils. So this one shows 7 turns, N equals to 7 and the current, and H equals to Ni, which is 7 times the current. And this is called the magnetizing force. And these red lines is the magnetic field B, like boy. Okay, I'm going to go through a couple of steps. This is the coil here. And it has, you can see 1, 2, 3, 4 turns, which means N equals to 4. And then I will pass current through it. And you can see the current in the coil. And the current is 5.8 or about 5.8 amps. So 5.7 amps. So now we will check the magnetic field. That's the next step. Okay, now I'm going to show you the magnetic field with the coil in the air. So I will connect the wires to the battery and you will see the response on the Gauss meter. This will be the magnetic field in air. See that? Okay, see right there, that's magnetic field in air. Now I have actually put a bolt here, a steel bolt with the coil again. And again, we have number of turns as 1, 2, 3, 4, 5 this time. And you will see when I connect it to the battery, the response will be much higher than the response in air. And see that it goes out of range. It's already out of range of the gauge. And this is what is called permeability. So now what I want you to understand is that you noticed that the magnetic field with the steel bolt was much higher than the coil with air in it. And that increase in the magnetic field is what is called permeability. And if I put a non-magnetic bolt, you will see it will be back to air. So if you have a coil with air, copper, aluminum, it's going to be the same response, which will be very low, which we call relative permeability of 1. And if you put a magnetic material like steel or iron, then the magnetic field is amplified, and that is called permeability. So let's go back to a bolt which is non-magnetic. Okay, this bolt is made out of a non-magnetic material. And in this case, the response is going to be the same as air. And I will connect it here and you'll see it's the same as air. and that's the magnetic field with this non-magnetic material in it, in the coils. And I take it out, and you'll see there is no change in the response because they're both non-magnetic, whether it's air or it is actually a non-magnetic material. So that's kind of shows you a demonstration of the coil solenoid method, which is used for longitudinal magnetism. And in this case, the driving force is the number of turns times the current, n equals to 7. This is called H equals to Ni. And then at the end, we have what is called the BH curve, in which the H is Ni, number of turns times the current, and B is the magnetic field. For air, it's going to be like this. You keep increasing the current, it's just going to be like that. And with the magnetic material, the response will be much more higher, and it will be here. And as you increase Ni, which is the current, it will just go here and taper off and get saturated. But when you actually reduce the current, it's not going to follow the same path. It actually will follow this path here. And when the current is zero, you will have some magnetic field. And this is called the residual magnetic field. So I hope I kind of gave you an explanation of this BH with some demonstration, very simple home demonstrations, so that you get an idea, because we learn all of this in the books, but you really have to see it to really understand what is B measured with the Gauss meter and the current produced by a simple home battery. Thank you so much.